Hello everyone, and thanks for watching Edupedia World videos. In this video we'll begin a new unit called Electromagnetic Waves, and this is the final unit for the broad topic electromagnetism. First we'll see a brief recap of everything we've learned so far, and everything we've learned so far can be categorized very neatly into 5 separate equations. The first equation will be our analog of F is equal to 1 by 4 pi epsilon naught this is equal to k q1 q2 by r square. This is the electric force between any two objects. From this was our starting point. From this we can define electric field, and from that we were able to deduce the Gauss law for electricity. So the first law will be the Gauss law for electricity. Cyclic integral of E dot ds, ds is the small area element, is equal to q enclosed by epsilon naught. This is the first one, right? This is called, now I'll just rub this. This is called Gauss law for electricity. Generally, when somebody says Gauss law, this is what they'll be meaning, although there is something which is called the Gauss law for magnetism, and we've seen that also when we learned that magnetic fields have no monopoles, there are only magnetic dipoles present. That means that the flux of the magnetic field through any closed surface is always zero, because there are no magnetic monopoles, right? This is often called Gauss law for magnetism. Now you see the pattern. What here we have done is we've taken the surface integral of electric field and surface integral of magnetic field. The next two equations, the third and fourth one, concern the line integrals of the magnetic and electric field. So the equation which we generally know as Faraday's law is EMF is equal to minus d phi b by dt. Phi b is the flux due to the magnetic field, but then E can be written as, this is the EMF. EMF in any loop can be written as integral of E dot dl, right? So this is called Faraday's law. Right. And finally we have Ampere's law. And just like these two are the surface integrals of electric and magnetic field, these two should be line integrals of electric and magnetic field. So this is the line integral of magnetic field, B dot dl, and we know that is equal to mu naught I enclosed. Now we started from F is equal to k q1 q2 by r squared. From that we proved this equation, and then we started from various points and proved these equations. The amazing thing is, these four formulas are the only thing that is needed to ultimately derive everything you've learned, except you need one extra formula which you've seen, and that formula is F is equal to Q times E plus V cross V. Because electric field and magnetic fields are of no use if you can't derive what the force is from the field, right? So these are the electric and magnetic fields. This is the way any particle would react in an electric and magnetic field. The force due to electric field would be QE, the force due to magnetic field would be Q times V cross B, the net force would be the resultant. This is called the Lorentz force law. And all you need is these 5 equations, and from these 5 equations you can ultimately derive everything we've done till now. Right. Now there is a little bit of problem in this. The fourth equation, Ampere's law, is not strictly correct. There is a small error in this, which was eventually fixed by the scientist James Clerk Maxwell. So let's look at what the error is. So what we have is a simple battery of, let's say, EMF E, and it is directly attached to the capacitor of capacitance C. Now it is attached at t is equal to 0. There will be some small resistances in these wires. Let me just create one if it's easier for you. So it will take some time for the capacitor to be charged. During that time, current will be flowing in this direction and it will be increasing in value. Right. Let's take a small loop within the plates of the capacitor like this. Right, the loop is parallel to the plates of the capacitor, and it doesn't have to be in the middle, it's somewhere between the region of the capacitor. Now, these currents would create magnetic fields. Those magnetic fields would create a circulation of the magnetic field here. Let's call this small curve S. Let's call the small curve L that is generally used. So in this curve L, cyclic integral of B dot dl is not equal to 0, right? Because there will be currents due to these there will be magnetic fields due to these currents. However, these currents only increase the charge on this plate and decrease the charge on this plate. These currents never actually make any charge go through this loop. So mu naught I enclosed is 0 for this loop, because through this loop there is no actual current flowing, right? This loop is an empty space, there is no wire flowing through this loop. So for this loop, integral B dot dl is not 0, but mu naught I enclosed is 0. So how does this come? Because Ampere's law should say that integral B dot dl is equal to mu naught I enclosed. So what happens is, actually there is a magnetic field created by these, but there is also an additional magnetic field created. Now if you remember closely, when we started talking about Ampere's law, I gave you one restriction. I said Ampere's law is valid as long as the electric field within the loop does not change. But that's not true in this case, because this will have some charge Q, this will have some charge minus Q, this charge will increase in magnitude, this charge will have the same magnitude in the opposite direction. So the electric field through this loop is changing, and hence the flux of the electric field, or the electric flux through this loop, is also changing. Right. So in that case, Maxwell did a correction to Ampere's law, and the final equation needs to read integral of B dot dl is equal to mu naught I enclosed plus mu naught epsilon naught d of phi e by dt. So you can take any loop in space. The circulation of magnetic field will be equal to mu naught I enclosed if d phi e by dt is 0. That is, the flux of electric field through that loop is not changing. The derivative of that with time is 0. If this is not true, then this is the actual equation. The first three equations are exactly correct. The first equation now we read as this, and this is called Ampere's law with Maxwell's correction. Right. Also, this term epsilon naught d phi e by dt, this is often written as id, or I'll write this on a new slide. So we have integral of b dot dl, cyclic integral over a loop, is equal to mu naught I enclosed plus mu naught epsilon naught d phi e by dt. And this term epsilon naught d phi e by dt is also referred to as id, which is called displacement current. And the I enclosed, the conventional I which we've seen up till now, which is actually the flowing of charge, not epsilon naught multiplied by the rate of change of electric field, is mostly then denoted as IC, called conduction current. This is the standard I which you've seen now. I'm only writing it as IC to distinguish it from the displacement current. Conduction current is an actual current. Displacement current is not an actual current. It's simply the epsilon naught constant multiplied by the derivative of electric flux with respect to time. With this, we can actually write it as cyclic integral of B dot dl is equal to mu naught times I conduction current enclosed plus I displacement current. Right. So this is another way of writing the fourth equation, and these are the four equations which ultimately govern all of electromagnetism. The surface integral of electric field is Q enclosed by epsilon naught. Surface integral of magnetic field is 0. Line integral of electric field is minus d phi b by dt, and line integral of magnetic field is written right here, mu naught times the conduction current through the loop plus the displacement current through the loop. This is obviously through the loop because the flux will be taken through the loop along which we are applying B dot dl. Now it changes one more thing slightly. It changes the continuity of electric current. Let's say we have some region and current I1 flows into that region and I2 flows out of that region. Then if we know for a fact that there is no charge accumulation within this region, then we can say I1 is equal to I2. If there is a third current I3, then we can say I1 is equal to I2 plus I3, because this is going in, these are coming out. This is only valid if there is no charge accumulation within this region. But what if there is some charge accumulation? Let's call this Q, and if there is some charge accumulation, then there will be a displacement current which will be equal to the rate of change of charge, right? And what we know is d phi e by dt, the rate of change of flux through this surface will be equal to d by dt of Q by epsilon naught, Q enclosed by epsilon naught, right? From that we can directly see epsilon naught d phi e by dt, which is equivalent to id displacement current, is equal to dq by dt, the rate of change of Q, right? It will be positive if there is charge entering, negative if there is charge leaving. So the actual equation will be I1 minus I2 minus I3 is equal to dq by dt, rate of change of charge, which is displacement current, which also is equal to epsilon naught times d phi e by dt. So if there is no charge accumulation in a region, then current going in is equal to current coming out. If there is charge accumulation, then it's natural enough the current going in minus current coming out is equal to the rate of charge accumulation, right? I didn't give you a proof for this epsilon naught d phi e by dt, but here we can actually see that epsilon naught d phi e by dt does indeed work like a displacement current. Right. Now let's look at in detail what happens in actual electromagnetic waves. So when electromagnetic waves flow from one point to another, we are assuming that they are flowing through vacuum. That means there is no actual charge present, just the waves are flowing. Now electromagnetic waves, by this point we know that electromagnetic waves can have many forms: radio waves, gamma rays, visible light, infrared and stuff, but all of those have been proven to be actually equal to electromagnetic waves which have been made by the variation of electric and magnetic field. So when light is flowing from point A to point B, what is actually happening is electric and magnetic field are varying in a sinusoidal manner from point A to point B. The generic equation for an electromagnetic wave is such: we'll assume that the electromagnetic wave is propagating in the positive x direction, this is the positive y direction, and this is the positive z direction. So the characteristics of an electromagnetic wave are the electric and magnetic field both are perpendicular to the direction of propagation and they are perpendicular to each other, right? So if this is the direction of propagation and we assume that y is the direction of electric field, then z automatically has to be the direction of magnetic field. The equations generally will be written as such: E is equal to E naught sine omega t minus x by c I cap. Sorry, not I cap, j cap. Right. So the electric field is a sinusoidally varying wave, and we've seen wave motion before. This omega t minus x by v or omega t minus kx, these forms we've seen before, right? So the electric field at some points is 0, at some points is plus E naught, at some points is minus E naught, but it is pointing in the y direction. So at some points it will point up and down. Then there is the magnetic field, which is given as B naught sine omega t minus x by c k cap. So this is what I said: if the direction of propagation is the x direction, electric field has to be perpendicular to the direction of propagation. We can choose any direction in the yz plane to be the direction of electric field. For simplicity, we choose the y direction to be the direction of electric field. If we choose the y direction to be the direction of electric field, then the magnetic field is perpendicular to the direction of propagation as well as to the electric field. So then electric and magnetic field are perpendicular to each other, and so we have this 90-degree angle between them, which means magnetic field has to point in the z direction, right? So a few simple points here: E is perpendicular to I hat. I hat is the direction of propagation. B is perpendicular to I hat, and E is perpendicular to B. Now this C, actually we don't need to worry about it. C is just the velocity of propagation of the waves. But when we actually found out the value of C, we found that it was exactly equal to the speed of light. And that was the first time when people made a conclusion that electromagnetic waves are actually made up of, we didn't call them electromagnetic waves, so now it sounds redundant saying electromagnetic waves are made up of electromagnetism. Before that it was just light, and we found out that light is actually made up of electromagnetic waves. Right? So these are the three equations. If I could for a second try to draw a good figure to explain to you the way this works, it will be something like this. Electric field will go like this. It will be 0 at this point, some value at this point, some higher value, some even higher value, some even higher value, low value, low value, low value, low value, 0, higher value, higher value, higher value, higher value, and so on. So at any point the electric field will be pointing in the y direction, but its magnitude will keep changing according to sinusoidal motion. Similarly, at any point of time the magnetic field will be pointing in the z direction, and it is in sinusoidal motion. And another important thing is electric and magnetic field are in wave. You can see that we have sign in both areas. That means when electric field is 0, magnetic field is 0. When electric field is maximum, magnetic field is maximum. So the magnetic field might be made something like this. I hope you can understand the figure. This is in the z direction. Then again back. So this is the sinusoidal propagation of electric field, and this is the sinusoidal propagation of magnetic field, which is perpendicular in the z direction. They're 0 at the same point and they're maximum at the same point. Right. Now, one thing that is generally the next step after this is we would like to show you that this electromagnetic wave propagating in the x direction, that's why we have x by c in both, electric field sinusoidally varying in the y direction, magnetic field sinusoidally varying in the z direction. What we would like to prove is that this particular system actually obeys the 4 equations we talked about: Gauss law for electricity, Gauss law for magnetism, Faraday's law, and Ampere's law with Maxwell correction. But in your course, only the qualitative treatment of electromagnetic waves is there, not the actual mathematical treatment. So I'm not going to prove it, but if you're a little bit familiar with mathematics and vectors especially, I would suggest that you try to prove that this electromagnetic wave actually does follow all these 4 equations. When we do try to apply all these equations and try to prove that it indeed does follow all these equations, we see 2 very remarkable results. The first result is E0 is equal to CB0. Again, I would prove this result by showing you that those electromagnetic waves follow the 4 electromagnetic equations, but that is not in the scope of your syllabus. So this is the first relation. You just now remember it. The electric field and the magnetic field, the magnitudes vary by a factor of C. The other equation we see will be C is equal to 1 by root of mu naught epsilon naught. And this particular equation is one of my personal favorites because this was the time when we were actually able to connect the two. We started with electromagnetism, then we came out to electromagnetic waves. We assumed that electromagnetic waves were sinusoidally varying. We assumed some speed c, which would initially have been denoted by v. We found out v is equal to root of 1 by mu naught epsilon naught. We calculated the values of mu naught epsilon naught, and it was a very strange coincidence. We saw that this speed turned out to be exactly equal to the experimentally measured speed of light, which is obviously, we'll study this later, much later in special relativity, is a fundamental constant and no object can travel faster than that. So we started from a completely different point of electromagnetism, but we were able to calculate and find out that the speed of electromagnetic waves is exactly the same as the speed of light. And we found out some other things as well, which led us to conclude that light is in fact made up of electromagnetic waves. So these 2 equations you should always remember. Let's see a few other things in regards to electromagnetic waves and the amount of energy they propagate. The energy density due to electric field, we saw this, is equal to half epsilon naught E square. The energy density due to magnetic field is equal to 1 by 2 mu naught B squared. right? Now, actually, if we try to solve these, this would come out to be half epsilon naught E naught square sine squared omega t minus x by c. And this would be half of epsilon naught, sorry, 1 by 2 mu naught b naught squared sine squared omega t minus x by c. Right. Now, if we calculated the average of the energy density due to electric and magnetic fields, the average of sine square theta is 1. Let me just show that to you. Integral of sine square theta from 0 to 2 pi will be, sine theta can be written as half of 2 sine square theta. 2 sine square theta can be written as 1 minus cos 2 theta, right? Integral of cos 2 theta will be 0, and we are left with half into 2 pi, and the denominator will be 2 pi because we wanted the average, so it will come out to be half. Anyway, this is something you should remember. The average of sine square theta and cos square theta over a complete cycle is equal to half, right? So the average energy density due to electric field is half of this. That will be 1 by 4 epsilon naught E naught square. This is E naught and this is E. Remember the difference. The average UB will be equal to 1 by 4 mu naught B naught square. But we know that E naught is equal to C B naught, right? And we know that C square is equal to 1 by mu naught epsilon naught. From that we can see, let's start from here. 1 by mu naught, we can write it as C square epsilon naught, right? So UB comes out to be 1 by 4. 1 by mu naught I'll write as C square epsilon naught, and C square B naught square can actually be written as E naught square, which is equal to the energy density due to the electric field. So this is an interesting result. The energy density due to the electric field is equal to the energy density due to the magnetic field, which is equal to 1 by 4 epsilon naught E naught square, which is also equal to 1 by 4 mu naught B naught square, right? And the total energy density, which is equal to obviously the sum of energy densities for electric and magnetic field, that is actually 1 by 4 epsilon naught E naught squared plus 1 by 4 mu naught B naught squared, which is also equal to half epsilon naught E naught squared, and is also equal to 1 by 2 mu naught B naught squared, because these two terms are equal. So the energy of an electromagnetic field can be written either in terms of the magnitude of electric field or magnetic field, or can be written separately. This is the electric field combination, this is the magnetic field combination, right? There are a couple other terms which you need to know about when you're talking about electromagnetic waves. The first term would be intensity. The definition of intensity is energy crossing per unit area per unit time, per unit time. Or another way of saying this would be power crossing per unit area, right? So let's see what that is. We have an electromagnetic wave traveling at a speed c, right? Let's consider a certain region and this particular surface. We'll be applying intensity for this surface. So what is the energy crossing this area in some time? Let's say the time is delta t. In delta t time, this distance will be c delta t, and every single particle or every single photon which is within this surface, within this volume, will end up crossing this in a time delta t, right? What is the energy density? That is half epsilon naught E naught square. So the intensity will be the energy per unit area per unit time. What is the energy? Half epsilon naught E naught squared into the total volume. Let's say this is area is A, so the total volume will be A C delta T divided by the area divided by the time. So this and this cancel. Ultimately we get half epsilon naught E naught squared C. Or a standard result which you should remember for all waves, not just electromagnetic waves, the intensity is equal to the energy density multiplied by the speed of light or the speed of the wave, right? In this case it comes out to be half epsilon naught E naught square C. These are just terms you need to know. For example, you'll get a question like, we have an electromagnetic wave which has an intensity of whatever value. And the moment you know what the intensity is, C and epsilon naught both are universal constants, so you'll know what the magnitude of electric field is. Right? Another quantity which is the momentum. Yes, so now we see that electromagnetic waves, even though they are not made up of any particles themselves except for massless particles called photons, which we'll see in modern physics, they still have some energy, some intensity, and even some momentum. In fact, if a door was smooth enough, all you would need to do was shine a piece of light on the door and it would move, because the light would impart some momentum. However, the amount would be very, very small. The momentum of an electromagnetic wave comes out to be equal to U by C. Right, we'll not prove this. Now this is important. U here is not the energy density, it is energy. Total energy of a wave. So if I strike an electromagnetic wave on a particular area, the total energy of the electromagnetic wave divided by the speed of light will be the momentum imparted. Remember, small u is for energy density or energy per unit volume. Capital U is for total energy. Right, so we've learned some things in regards to electromagnetic waves, how to calculate the energy density within any volume, how to calculate the intensity, and now we know the momentum of any electromagnetic waves. There's one more thing which we learned when we were talking about waves, and we saw one big difference between transverse and longitudinal waves, which was that transverse waves can be polarized. And electromagnetic waves are an example of transverse waves because the vibration is perpendicular to the direction of propagation. Right, this is the same like we had in a string. The direction of propagation are the y and z, the direction of disturbance are the y and z directions, but the direction of propagation is the x direction. Now, the polarization vector is a unit vector, and it is a vector in the direction of electric field. We could have chosen magnetic field, but we chose electric field. This is the direction of polarization. So if a wave travels along the x direction, in that case the polarization can be anything in the yz plane. We, as it happens, chose the direction of electric field to be the y direction. In that case we had a simplified thing where y direction had an electric field, z direction had a magnetic field. In that case we would say that the wave is polarized along the y direction. However, if the magnetic field was along the positive negative y direction and the electric field was along the z direction, then we would say the polarization is along the z direction. If we had our eyes at this point and we were looking towards the x direction, then we would see a circular aperture where polarization would be defined like this. Polarization for positive y and negative y won't be different because electric field vibrates along the y direction both in positive and negative. So this is how the polarization would be shown. If the polarization is along the z axis, then this is how the polarization would be shown. In that case, going inside the plane is the x direction. Then there are other forms as well. You can have the polarization at an angle, right? Maybe the electric field is at 45 degrees between y and z. The magnetic field is perpendicular to that at another 45 degrees. Then we would say the wave is polarized at 45 degrees to the y-axis, right? So this would be the direction of polarization. Often you can even have waves in which we saw in this case that electric and magnetic fields were in phase, but it is actually possible to have electric and magnetic fields not in phase. They can lead each other or be behind each other by some phase, which would lead to the polarization vector actually rotating. You can have a polarization vector that is at one point this, in the next instant you move a little further, it's like this, then it's like this, and it's like this. So that polarization is denoted like this, a clockwise polarization. That means the electric field is rotating in a clockwise direction. Of course, there is another polarization, this, which is called the anti-clockwise polarization. Right. So there's linear polarization, these are called circular polarizations, and there are elliptical polarizations, which you don't need to worry about, they're beyond the scope. But the important thing to know is polarization is defined as the direction of electric field. Every electromagnetic wave has a particular unique direction of polarization. It has to be perpendicular to the direction of propagation, and it is generally chosen to be the direction of electric field. Right. This completes the mathematical aspect of electromagnetic waves, but there's one small thing left. Let's study a little bit about how electromagnetic waves really behave in actual life. This video is getting too long, so I'll do that in the next video.